Unlike linear equations, with linear inequalities, we usually graph the solution set. And the reason we graph the solution set is because there's not one, two, three, or 500 solutions. There's technically infinitely many solutions to each one of these. Remember, we are doing mathematics in the real number system. So we're considering all possible real numbers, which is essentially anything that could be written as or approximated by a decimal. So for example, if we wanted to graph the solution set to x is greater than or equal to 7, 8 is technically a solution because 8 is greater than 7, so is 9, so is 10, but so is 8.3812111587, and so is 7.0000001. So there's infinitely many solutions. Now to graph the solution set, we're going to graph it on the number line because it's one-dimensional. You're only talking about x values. There's not y values included. When you draw your number line, please always mark a 0 point. And of course, don't forget the 0 point divides up the negative numbers, which would be to the left, and the positive real numbers, which would be to the right. So graph the solution set where x is greater than or equal to 7. So 7 is a boundary point. So we need to note that on the graph. Now, technically, we could count by ones out to here, out to 7, but I'm confident that you guys know how to do that. So at this point, you can just put a tick mark and put 7 there. The only thing that I want to make sure you do not do is certainly do not put 7 over here. You have your negative real numbers over here and your positive real numbers over here. Now we want the values of x that are greater than or equal to 7. So that means over here, 8, 9, 10, 11, so on and so forth. But we're not going to just draw some dashes or some points in here because as we said, we're talking about any real number. So 7.0001 or 8.38125811 is a solution. So we're going to draw a continuous line. And you'll see I typically write the solution set above the number line just because it can get a little bit messy down here. So I'm going to write it up here. So our solutions are found to the right of 7. Now, do they stop? At some point, like if I get up to 100, does that mean there are no more solutions beyond that? No, all the numbers that are greater than 100 are certainly greater than or equal to 7. So they go on forever. And I can't draw a line forever. So what I do is put an arrowhead here to let people know that this is going on forever in that direction. Now, as we just mentioned, this includes like 7.001 or 7.005 or 7.8,000 zeros followed by a 3. So all the numbers all the way up to 7 are solutions. So we got to let people know whether 7 itself is a solution. And as we know, x is greater than or equal to 7 means that x can be 7. So the way that you let people know that 7 itself is a solution is you put a solid dot right at that point. If you want to include that endpoint, you put a solid dot, which is called a closed circle. Or if you want to exclude that endpoint, you put an open dot, which is called an open circle. So we're going to put a closed circle right here at 7, meaning that 7 itself is actually a solution. This is the complete graph to the solution set of x is greater than or equal to 7. Let's do each of these three as well. So graph the solution set to x is less than negative 3. So negative 3 is an important boundary point. Plot that point. Clearly, negative 3 would be to the left of 0. Again, you don't have to count out to negative 3. You can just place a negative 3 at a spot there. And then we want the numbers less than negative 3. That's the numbers that are located over here. The numbers like negative 5, negative 100, those are less than negative 3. So the solutions are going this way, and they don't stop. All the numbers that way are less than negative 3. So we're going to put a little arrowhead there. Now the question is negative 3 itself a solution? Because remember, negative 3.00005 is technically less than negative 3. So it's not like I can just start this at negative 4. Remember, there's infinitely many decimals between negative 3 and negative 4. So it's not like I could just start it at negative 4. I got to start here from negative 3. So how do I let people know, though, whether I want to include negative 3 or not? Again, that's where this notation comes into play. And because x is less than negative 3, it can't equal negative 3, that means I want to exclude that endpoint. So I'm going to put an open circle here at that point. Let's try this one. Now we're dealing with a compound inequality. Again, x is between negative 2 and 1, including 1 because of the equality there, but excluding negative 2. So there's two important boundary points, negative 2 and 1. Let's plot those. Of course, negative 2 is to the left of 0. 1 is to the right of 0. And let's just start with those endpoints. X cannot be -2 because you don't have the equality there. So I'm going to put an open circle over the -2, and then X can be 1 because you say X is less than or equal to 1 here. So I'm going to put a closed circle over here at 1. Then all the other solutions aside from this one point are between these two, right? X is between -2 and 1, so I draw a line connecting these two. Now notice here, with this one, I didn't put an arrowhead anywhere. This arrowhead means that goes on forever in that direction. This arrowhead means this goes on forever in this direction. Here, you're not going on forever in either direction. It's bound on both sides, so it's stuck here in the middle. There are still technically infinitely many real numbers in here. Right? Negative 0.3851111, for example, is the solution. So even with compound inequalities, the reason we graph them is because there's still infinitely many solutions to them as well. Let's do this last one, and this one we need to be careful with. All right, 4 is greater than x. So clearly 4 is an important boundary point. Make sure you mark a point to the right of 0 because 4 is positive. Is 4 itself a solution? Well, it says 4 is greater than x, so since it does not have the equality here, that means 4 is not a solution. So we're going to put an open circle there. However, where are the solutions from there? Are they to the left of 4 or are they to the right of 4? A common error is students often look at this and say, oh, greater than, that's the greater than symbol, that means go to the right. That is actually not true. The only time the greater than symbol means go to the right is if the variable is also on the left-hand side. So let's first rewrite this based on the previous screencast with x on the left. How would you write 4 is greater than x? How would you write that with x on the left? Well, 4 is greater than x is the same thing or is equivalent to x is less than 4. Now, if you look at this, this says x is less than 4. So we want the numbers less than 4, which are to the left. And remember, they don't stop at 0. The negative numbers are less than 4 as well. And so they go over here to the left. Make sure you realize that this right here is not part of my solution. If you feel one like this will give you trouble, then you should probably rewrite the inequality first with the variable on the left-hand side. This is not mandatory to do this. You could go right to drawing the solution set, but sometimes students may need to see this for a while until they get used to it. Now, notice for each of these 4 inequalities, the x is already isolated. I don't ever ask you to solve an equation where the x is already isolated. So you're not going to have inequalities where the x is already isolated. So there is some computational stuff we have to do as well with this. We'll see that on the next screen. We need to be able to solve inequalities where the x isn't already isolated. So quickly, remember we discussed equality. If you had 2x equals 6, that's the idea of having 2x on one side of the seesaw and 6 on the other side, and then it would be balanced because they're equal to each other. It's like these two kids are the same weight. Where we have inequality, you don't have the balance. One side is heavier than the other. So we're going to keep that in mind as we go through how to solve these equations. So what if you had 2x is greater than 6? In this case, I'm going to write the 2x down here and the 6 here. 2x is greater than 6. We're going to treat that like 2x is heavier than 6, so 2x would be lower. So if this was an equation, what would you do? Well, if you were over here, the way to solve for x would be to divide both sides by 2. Because if you cut both of them in half, then those resulting pieces are still the same weight. Over here, would that be true? If 2x is heavier than 6, if you cut both of them in half, would the resulting parts, would this over here still be heavier than the resulting part over here? Yes, because half of a bigger quantity is still heavier than the half of the smaller quantity. So it is completely legitimate to divide both sides by 2, and that's how we would solve this inequality. So we would divide both sides by 2, and we would be left with x is greater than 6 divided by 2 is 3. So we have x is greater than 3. That is the solution set to 2x is greater than 6. On this particular screen, we are not going to spend time graphing the solution set. We'll get to some examples where we'll solve the inequality and graph the solution set. We first just want to see what are legal things we can do with linear inequalities. So let's solve x plus 2 is greater than 6. Well, if x plus 2 is greater than 6, we could consider that like x plus 2 is greater than 6 or heavier than 6. That would mean the x plus 2 would be the lower side. So if this was an equation, in order to solve this, we would want to subtract 2 from both sides. Well, if you took 2 pounds off of this kid and 2 pounds off of this kid, would this kid still be heavier? Yes, because if you take the same amount off of both of them, the heavier kid will still have more weight than does the lighter kid. So it's completely legitimate for us to subtract 2 from both sides, just like we would have done with equations, and we get x is greater than 4. That's the solution to this inequality. And again, these are linear inequalities because the x is only being raised to the first power. What if you had x minus 2 is greater than 6? Well, without erasing this again, same idea. If x minus 2 was here and 6 was here, and you would want to add 2 pounds to both sides. If you added 2 pounds to both sides, you'd still have the heavier kid would be heavier as a result. So you can add 2 to both sides of an inequality and still get the same result. So we're getting equivalent inequalities. This inequality, x is greater than or 8, is equivalent to this inequality, x minus 2 is greater than 6. But the value of this one is that x is isolated. And finally down here, you have x divided by 2 is greater than 6. If this was an equation, what you would want to do to isolate x is multiply by 2. But again, if you've got the heavier kid over here than over here, if you doubled the weight of this side and doubled the weight of this kid, the heavier one would still be heavier. So it is completely legitimate to multiply both sides by 2, which would then give us x on the left-hand side is greater than 6 times 2 is 12. So as of now, each one of these we just solved, it looks exactly the same as solving linear equations. However, this is not the complete story. We have to be careful.